Hi all, welcome back to my channel. Subscribe before watching my video.
Welcome to Unit 2, where we dive into combinational logic. I'm A. Sindhu Devi from the Computer Science and Business Systems Department at Jerusalem College of Engineering. Together, we'll explore the building blocks of digital circuits and how they work without memory, just pure logic at play. Let's get started. Let's talk about multiplexers, or MUX for short. Think of a MUX as a digital switchboard. It takes data coming in from several different inputs, then channels just one of those signals through a single output line. This way, multiple data sources can share one pathway without interfering with each other. It's a clever way to manage information flow efficiently in digital circuits. Here, we see a visual representation that brings the concepts we've discussed to life. This diagram helps us connect the dots, showing how each part interacts and supports the whole. It's a roadmap, guiding us through the process step by step. As we move forward, keep this structure in mind. It's the foundation for everything we'll explore next. Let's take a moment to understand how this all works. We'll break down the process step by step, so it's clear what's happening behind the scenes. From start to finish, each part plays a role in making the whole system function smoothly. By the end, you'll see how the pieces fit together and why it all comes together the way it does. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Multiplexers play a crucial role in making systems more efficient and cutting down on hardware costs. Think about telecommunications. Instead of laying hundreds of cables across oceans for each phone line, a multiplexer combines them all into one high-speed fiber optic cable. At the other end, a demultiplexer separates the signals again. Inside computers, multiplexers help CPUs pick the right memory address or move data between registers using shared pathways. And in everyday life, they decide which audio source, like Bluetooth, aux, or radio, plays through your car's speakers. These are just a few real-world examples of how multiplexers keep things running smoothly. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about the 2-to-1 multiplexer, the simplest kind of multiplexer there is. It takes two data inputs, but only one output line. A single select line decides which of those two inputs actually makes it through to the output. Think of it like a switch that flips between two signals, sending just one forward at a time. This basic concept is the foundation for more complex multiplexers down the line. Let's take a closer look at truth tables and logic functions. A truth table lays out every possible input combination for a logic function, showing the resulting output for each. It's a simple, clear way to visualize how a function behaves. From this, we can derive the logic function itself, a concise expression that captures the relationship between inputs and outputs. Together, these tools help us understand and design logical systems with precision. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Now, let's focus on the 2-to-1 multiplexer logic simulator. This tool lets us test how a multiplexer selects between two inputs based on a control signal. It's a fundamental building block in digital circuits, helping us direct data efficiently. By simulating this logic, we can understand how decisions happen at the hardware level and ensure our designs work before moving to physical implementation. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about the 4-to-1 multiplexer, often called a 4-1 MUX. It's a digital switch that selects one of four input signals and forwards it to a single output line. Think of it as a traffic controller, directing data from multiple sources, but only one at a time. The selection is controlled by two input lines, which decide exactly which input gets passed through. Multiplexers like this are key in simplifying complex circuits and managing data efficiently. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's take a closer look at how this all comes together using logic gates. These tiny building blocks are the foundation of digital circuits. Each gate performs a simple function, like AND, or not, but when combined, they create complex decision-making systems. By wiring these gates in the right way, we build the logic that drives everything from basic calculations to advanced computing. Understanding this helps us see the inner workings behind the technology we use every day. Now, let's dive into the 4-to-1 multiplexer logic simulator. This tool lets us explore how a multiplexer selects one input out of 4, based on control signals. It's a great way to see digital logic in action, how data flows, how decisions happen inside circuits. By simulating this, we get a clearer picture of how complex systems manage multiple inputs efficiently. It's a fundamental building block in digital design, and this simulator brings it to life. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about the 8-to-1 multiplexer. This device takes 8 different input signals, but only lets one of them pass through at a time. We use select lines to decide which input gets through. It's like having 8 different roads, but only one gate that opens at a time. Multiplexers help us manage multiple data streams efficiently, saving space and simplifying circuits. They're essential in communication systems and digital design. Understanding how an 8-to-1 multiplexer works is a key step in mastering these concepts. Let's take a closer look at the truth table. It's a simple but powerful tool that shows all possible input combinations for a logical operation, and the resulting output for each. By laying out every scenario, we can clearly see how a logical statement behaves. This helps us understand complex logic step by step, making it easier to analyze and design digital circuits or solve logical problems. The truth table is the foundation for clear, precise reasoning in logic. Now, let's talk about Boolean logic expressions. These are the building blocks of decision-making in computing. They combine simple true or false values using operators like AND, OR, and NOT. By stringing these together, we create complex conditions that control how programs behave. Understanding Boolean logic helps us write clearer, more precise instructions, the foundation of all programming decisions. Now, let's talk about setting up the internal gate. This step is crucial because it controls the flow of information within the system. Getting it right means smoother operation and fewer errors down the line. We'll walk through the key components, how they connect, and what to watch out for to ensure everything runs seamlessly. It's all about creating a solid foundation that supports the rest of the process. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's look at how we can build an 8-to-1 multiplexer using smaller building blocks. We start with two 4-to-1 multiplexers, each handling 4 inputs. Then, we use a 2-to-1 multiplexer to select between the outputs of those two. This setup breaks down a complex problem into manageable parts, making design simpler and more modular. It's a classic example of combining smaller components to create a larger, more flexible system. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Now, let's dive into building an 8-to-1 multiplexer using only 2-to-1 multiplexers. We're essentially creating a tree structure, where each stage combines smaller multiplexers to handle more inputs. Starting with pairs of inputs, we merge them step by step, doubling the number of inputs handled at each level. This approach shows how complex logic can be constructed from simple building blocks, a powerful concept in digital design. It's all about layering and connecting these small units efficiently. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about a quadruple 2-to-1 multiplexer. A common chip you might know as the 74LS157 or 74HC157. It's basically 4 separate 2-input multiplexers packed into one device. This lets us choose between 2 different 4-bit data sources and route that selection to a single 4-bit output bus. All of this happens using just one shared select line and an enable line, making it efficient and compact for handling multiple bits at once. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's take a closer look at the key pin functions of the 74157 chip. Understanding these pins is crucial because they control how the chip selects and routes data inputs. Each pin has a specific role, from selecting which input to pass through, to enabling or disabling the chip's output. By mastering these functions, we can effectively use the 74157 in our digital circuits, making data selection both precise and efficient. Let's break down the data inputs and control signals for this chip. We have 2 sets of 4-bit inputs, called buses, a 0 through a 3, and B0 through B3. The select line, labeled S, decides which bus connects to the output. If S is 0, the A inputs pass through. If S is 1, the B inputs do. Then there's the enable pin, it's active low, meaning when it's low, the chip operates normally. When it's high, all outputs go to 0, no matter what the inputs are. Let's look at some common applications of multiplexers. First, bus routing. This means switching an output bus between 2 different microprocessors or memory banks, deciding which one talks at a given time. Then, data selection, multiplexing 2 nibbles, or 4-bit chunks, before sending them down a single transmission path. Multiplexers also work as function generators, acting like a central hardware switch to modify data streams before they reach the arithmetic logic unit. And finally, display multiplexing, rapidly alternating data between multiple 7-segment LED digits to share a single decoder driver chip. These are just a few ways multiplexers keep systems efficient and flexible. Let's explore how to build a 16-to-1 multiplexer using smaller 8-to-1 multiplexers. Instead of designing a big multiplexer from scratch, we combine 2 8-to-1 multiplexers to handle the inputs in halves. Then, a third multiplexer selects between their outputs, based on the highest order select bit. This approach simplifies complex designs by breaking them into manageable parts, a classic example of modular thinking in digital circuits. Let's take a closer look at the structural setup, the foundation that holds everything together. This is where we organize the key elements, define relationships, and build a framework that supports the entire project. Without a solid structure, even the best ideas can fall apart. So, understanding how to set up this framework is crucial for success. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about the Demultiplexer, or DEMUX for short. It's a digital information processor that takes a single input and directs that data to one of many outputs. How does it decide where to send the data? That's where the control lines, or select lines, come in. They act like a traffic controller, guiding the input to the right output. The number of these control lines actually sets how many outputs the DEMUX can have. It's a clever way to manage data flow efficiently. Let's take a look at the general block diagram of a demultiplexer, or DEMUX for short. This diagram shows how a single input signal is routed to one of several outputs, based on select lines. Think of it like a traffic controller, directing data down the right path. Understanding this layout helps us grasp how DEMUX devices manage data flow efficiently in digital circuits. It's a fundamental concept that powers many communication and processing systems. Let's take a closer look at the 1-to-4 demultiplexer, or 1-4-DEMUX for short. This device takes a single input and channels it into one of 4 outputs, based on the control signals it receives. Think of it as a traffic director, directing data down just one path at a time. It's a fundamental building block in digital circuits, helping us manage and route information efficiently. Understanding how it works is key to mastering more complex systems. Let's break down the 1x4 Demultiplexer. It has a single input, called I. Then, there are two selection lines, S1 and S0, that decide which output line gets the input signal. Finally, there are four output lines, labeled Y3 through Y0. The truth table shows how the input routes to each output depending on the selection lines. This setup lets us control where the input goes, using just those two selection bits. Here, we see a table that maps selection inputs to outputs in a clear pattern. The inputs, labeled S1 and S0, determine which output line Y3 through Y0 becomes active. When both inputs are 0, only the last output is on. Change one input, and a different output lights up in sequence. This setup is fundamental in digital circuits, helping us route signals precisely where they need to go, based on simple binary choices. It's a neat way to control multiple outputs with just two inputs. Let's break down how a 1x8 Demultiplexer is built. It's actually made by combining two 1x4 demuxes and one 1x2 demux. Together, these components handle two input lines and split the signal into 8 outputs. The truth table here shows exactly how each input corresponds to the outputs, helping us understand the logic behind the signal routing. This setup lets us control which output line carries the input at any given time. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Here, we see a clear example of how selection inputs control outputs in a digital system. The three inputs, S2, S1, and S0, act like a code, determining which one of the outputs from Y0 to Y7 will carry the input signal. Only one output is active at a time, matching the binary value of the selection inputs. This table shows the fundamental logic behind multiplexers, routing signals efficiently based on the selector bits we provide. Let's break down how a 1x16 Demultiplexer is built. Instead of designing it from scratch, we use smaller building blocks, two 1x8 Demultiplexers and one 1x2 Demultiplexer. This setup lets us manage two input lines and direct the signal to one of 16 outputs. The truth table here shows exactly how each input combination maps to the outputs, making the logic crystal clear. It's a smart way to scale up complexity using simpler parts. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Here, we see a table that maps selection inputs to their corresponding outputs. The inputs, labeled S3 through S0, represent different binary combinations. Each unique combination activates a specific output line, from Y0 up to Y15. For example, when all inputs are 0, only Y0 is active. As the inputs change, the active output shifts accordingly. This kind of mapping is fundamental in digital logic, helping us understand how selectors control which output is triggered. Here, we see a detailed matrix, a grid of zeros, ones, and a few standout letters. This kind of table often represents data patterns, connections, or states within a system. Each row and column tells a part of the story, showing how elements interact or align. While the specifics might look complex, the key takeaway is how structured data can reveal underlying relationships, helping us make sense of intricate information step by step. Let's talk about the DEMUX, a device that really boosts communication efficiency. It takes data from one input and sends it out to multiple destinations. Think of it as the opposite of a multiplexer or MUX. While the MUX combines signals, the DEMUX separates them, decoding mixed data into distinct outputs. This separation is key for managing complex signals. The advantages of the DEMUX come from this ability to organize and distribute data clearly and efficiently across different channels. Let's talk about some drawbacks of the DEMUX. One key issue is bandwidth wastage, because it splits refined data into different channels. Sometimes these channels overlap. That overlap can cause signal loss, which is a real problem. Another challenge is synchronization. When channels overlap, it can delay the entire process, throwing off timing and slowing things down. So, while DEMUX has its uses, these disadvantages are important to keep in mind. To wrap up, DEMUXs play a crucial role in designing ALU circuits and handling parallel data segments. They take the output from a MUX and convert it back into original inputs, helping to verify and store data efficiently. Whether in computing or broadcasting, DEMUXs separate signals into individual channels, making them essential in many systems we rely on every day.
Thank you for watching my channel. Please do share, like and subscribe my channel.